Thank you, Martin. Thank you. So, just a quick cleanup from last session. A question from Cielo. She asked me, I guess I didn't clarify enough this path ordered business. If you recall, we were trying to solve the parallel transport equation in Yang-Mills theory. We found a perturbative solution, and at one point we encountered an integral, the solution to second order. This will generalize to other orders, but we encountered an expression of this kind. And then we have some function f, which was basically the gauge field along the tangent vector to the curve, if you recall, but it doesn't matter, it's just some scalar function, s prime. And then the same function, this is important, on s double prime. Okay? And I said that this was 1/2 of the double integral from 0 to s ds prime, and then the second integral, if you notice, goes from 0 to s prime. So that means that s double prime is smaller than s prime, right? By definition. So that means that this is ordered, this is like time ordering in quantum field theory, right? So the future, and this is a political slogan if you want, the future is to the left. Okay? No, you can vote whoever you like. But this is bigger than this, okay? So this is important. But then you can write this as 1/2 of the integral from 0 to s. So not necessarily s double prime smaller than s, right? So there will be part of the range where this variable is bigger than this one. But then we wrote path ordered product of f of s prime and f of s double prime. Okay? And this p is simply equal to f of s prime, f of s double prime, if s prime is bigger than s double prime, and then the order is reversed. If s prime is, or let's write it like this, s double prime is bigger than s prime. Okay? And this identity is just a geometric, it's, when you plot it, it's straightforward. This just means that if I have so this is a double integral, right? So it's an integral of the plane. And if you plot s double prime here and s prime, the original integral is from 0 to s on this variable. So let's say that's s. Okay? And then the second integral goes from 0 to s prime. So this is the curve s equals s prime. I'm sorry, s double prime equals s prime. Right? So it's a straight line. So the integral is over this region. Right? We're integrating over that region. And then the observation is that I can simply double this and integrate on this other region. Right? But I need to keep in mind that because here, so here s double prime is smaller than s. Here s double, let me write like this. Okay, so here s double prime is bigger than s prime, right? So in order to make sure that always the first factor is bigger than the second one, I introduce this path ordering operator, right? So then now it makes sense that this integral, which is already path ordered, so I could put a p here if you want, and nothing happens, right? Because it's already ordered, and you will never find s double prime bigger than s prime, so the p is redundant. But then if I double the integral, that's why there's a factor of 1/2, I need to make sure that now, whenever s double prime is bigger than s prime, these things are reversed. Right? And you can imagine for fermions, this has a minus sign. Okay? So it works pretty much the same as time ordering in quantum field theory, except that this is path ordering because it's only a one-dimensional integral. So that was left from. Yes?
So, when we introduce this field, we're saying that f's are like operators that you have to commute.
In this case, they're functions, but they could be operators. Actually, they are operators. I'm thinking classically, but there's no problem that this translates to the quantum theory just fine. Remember that these were already matrices, so they were already non-commuting functions. So they're non-commuting because they're gauge fields, but they could be non-commuting also because they're quantum fields. So the argument is the same. Okay, so what we found then was that the solution to this equation, so x dot mu d mu phi equals 0 could be written as the path-ordered exponential of I g Young Mills times the integral of over ds of x dot mu a mu times, so this would be phi of s. So this is our, let's say, our matter field transforms in the fundamental of SUN, if you like. This would be the Higgs, this would be quarks, whatever field you want. And then this acting on some constant of phi 0. Okay, so that was the answer, and then that motivates giving this guy a name. Okay, so this is our famous Wilson loop. Yes?
What do you mean by S in the argument of phi?
This is along the curve, so this is finding a curve, it's mu of S, and I'm solving this equation along that.
Because you integrate over S, so it's a functional of the curve.
Yes. Yes. Of course. This depends on the curve I'm choosing. Yes. And that's actually, perhaps I should emphasize that. So Breno's comment was that this is a function of the curve. Depending on which curve I choose here, I'll get a different solution, obviously. And then to make it explicit, this will depend on which curve I choose. Okay? So that's the, let's say, the mathematical motivation for defining this Wilson. So I gave you the physical motivation. You can think of what's in the exponent as the effective action of this probe particle when you go around a closed loop, or you can think of it more mathematically as some sort of parallel transport. Yes?
There's another motivation for the Wilson line, for example. If you want to compute the correlation function between phi at point x and phi dagger at point x and phi at point y, it's not a gauge invariant. But if you put a Wilson line connecting y with x, that's gauge invariant. So
yes. So that's what I'm going to do. Actually, I'm not going to do the calculations because I want to move through the material I have. But the next question is, how does this transform under gauge transformation? And that gives another motivation for defining this guy. So how does a Wilson line transform under gauge transformations? So you can do this in different ways. So by the way, so this is, yes?
What does represent S in the phi S?
Here?
Yeah. No, in the phi S. Phi.
It's the parameter along the curve.
Okay. Should be, independent of
No. That was Brenner's point. So this equation depends on the path that I choose to solve for phi.
The function of the path.
Yes,
The path of the parameter. It's like
it's a functional of the path.
not of
And the path is a function of the parameter.
Okay, but you can reparameterize.
Of course. No, but this is representation of invariant.
Yeah, okay. Yes. So, but that represents the S. No, in the phi.
Ah, okay, I'm sorry.
Should be a function of
It should be GS prime, maybe.
No. Sorry. Thank you for the observation. I made a, no. Like they say to the kids in the internet, I made a boo-boo. Thank you. Sorry, thank you. Thank you. Yes, because this is from one point s equals 0 to some arbitrary point here. Thank you. This is just the old habit of writing the Wilson loop. So this is a Wilson line, okay? And in a moment I will introduce the Wilson loop where this line is closed, and then, of course, that will not depend on S. So thank you, Rodrigo, for that. So I will not show this, but so remember, we know how the gauge field transforms, okay? We know how the matter field transforms, and you can show that the transformed Wilson loop will just be the group element, the gauge group. Okay, and this is also of course depends on S as well. Okay, so thank you, Rodrigo, for making sure I get things right here. So the Wilson loop depends on S. So it actually depends on the two endpoints, right? It's just that I set one endpoint to 0, but it actually depends on both. Okay, I just chose to put one of them at 0. So then let's say, just to be very clear here, so this goes from 0 to S. So then I could write this more symmetrically like that. So you can show that if you do a gauge transformation, then the Wilson line will transform like that. And the proof, you can take the path order exponential, expand it order by order, do a gauge transformation, and then find that you get a total derivative and things like that. So that's one way, but that's very messy. The other way is to solve this equation again and show that this guy solves the same equation, but gauge transformed. So if you plug in phi prime and a prime, of course, and you solve this again, so that there'll be a different equation because now we have a different gauge field. And then you will see that if this guy solves that guy, then this guy solves the same equation but with a prime gauge field. Okay? And because the first order differential equations have one solution, then that's the only solution, right? So this is a very important property, and it's what Breno was saying. So now you have a thing, an object that transforms nicely under gauge transformation, because if you see, this is like a tensor. So you see one factor of the transformation on the left, the inverse on the right, and tensors are nice to construct invariants, right? Scalars. So Breno was saying that you could put a Wilson line in between two local operators to get a gauge field. So that's another motivation. All right. Now, notice that if the path or the curve is closed, okay, then W is covariant. In the sense that if this point is the same as that point, right, you get the same gauge transformation on the left and on the right. Okay, obviously the one on the left is G and the other one is G inverse, but they're both evaluated at the same point. So now I'm thinking of defining the Wilson line. That's my curve C. So this no longer depends on S, no longer depends on the initial and final points because they're the same, but it still depends on the path that I chose. Okay? So this will be W of C. Okay? And then the final step is if we take the trace of the Wilson line, or sorry, of the Wilson loop, that will be gauge invariant because the trace is cyclic and this guy will cancel with that guy when I take the trace. Okay? So finally, this guy, and then, so I'm gonna, I'm abusing notation here because I already used W for this guy. I'm gonna use W again for the trace of that guy. Okay, so sorry for the notation, but, so I'm gonna take a trace here of the path order exponential of I, G in mils, and now I get a closed curve.
Sorry, Professor?
Yes.
You might have already explained this, but I got a little bit lost. How do you know that the Wilson loop transforms with that form specifically from looking at the Wilson loop definition?
So you could do it from the definition here, and then expand the exponential order by order.
Okay.
Take into account the path ordering that I explained. Do a gauge transformation on the gauge fields.
So
But that's very messy. At first order it's trivial because you get a total derivative, but then it gets messy. But you can use that and show that that's gauge invariant. Or sorry, it transforms like that. The easiest way is to remember that this guy is a solution of this equation.
Yes.
Right? So then solve this equation with a new gauge field.
Okay.
And plug in this ansatz, and you will find that this solves the equation with the new gauge field.
Okay, so that's
then
like checking that it works.
That's the shortcut, of course. I wouldn't have thought that myself the first time, but that's the short way, and it's the easiest way actually. So it's not missing. Okay. So the point is that this guy is gauge invariant, and therefore it's an observable. Okay? So observables are gauge invariant in gauge theories. This guy is gauge invariant and it should be observable. And in fact it is, and there's many applications. The best known is the Aronoff-Bohm effect, where you have a solenoid. So you get a, if you remember your electromagnetism class, the infinite solenoid has the magnetic field is localized inside the solenoid and it's zero outside. Okay, but still, if you put a probe particle, the probe particle will feel the potential A, and the potential A is not zero outside, even though it's pure gauge. Okay, but it's not zero because it has to be continuous and inside and outside the solenoid, etc. So this quantity captures the fact that there's a non-trivial gauge field inside the solenoid. So if you didn't know there was a solenoid there, but if you had a Wilson loop machine, you could compute the Wilson loop around the solenoid, and it'll be non-zero. Okay, it'll be non-trivial, and that would be counterintuitive because outside the solenoid, there's no magnetic field. So you would think that A is equal to zero, but it's not. Okay, so that's one application. The other one is this can act as an order parameter for confinement, because you can show if you take a Wilson loop that has this form. Okay, you go around a path that is a rectangle, and you take the rectangle to be very, very, very tall. You can show that in the limit when the rectangle is very tall, what you're computing is the effective potential between the two particles between the particle that goes up and the particle that goes down. So the particle that goes down is traveling backwards in time, but you can think of it as an antiparticle traveling forwards in time. So you're computing basically what's called the quark-antiquark potential. Okay? And then if you're in a theory like, let's say, QED, this would be the electron-positron potential, and guess what you find? You get 1 over L. The expectation value of this Wilson loop goes like 1 over L. Okay? So this would be, the Wilson line will be like E, or the expectation value of the Wilson line, e to the minus B effective, and you will find that B effective goes like 1 over L, which is the Coulomb potential. But then in QCD, you expect this to be linear in L, and that's called the area law, because this will always be proportional to the height of the rectangle, which is infinite, and then you get something that's linear in L, so you get T times L, that's the area of the rectangle, and that is a signature of confinement. Because now the potential, instead of decreasing like 1 over L in Coulomb, it increases with L. So you get a constant force. So the further you stretch the two particles away, the bigger and bigger the potential energy becomes, and at some point it's favorable for the two particles to become jets and create more particles. Okay, so that's a signature of confinement. So there you have two applications. So in the Maxwell theory, actually, you can compute this straightforwardly because it's a free theory. So in the abelian case, and you can do this either using perturbation theory and Feynman diagrams. So you can. So what we're after is really this guy. Okay. So it's the VEV of this guy. So the VEV means a path integral over all possible fields. Blah blah blah. So there will be a path integral over the gauge field A mu. So then to first order you get 1. To second order it's linear in A mu. So the VEV of A mu is 0, so it doesn't contribute. To second order, now you get A mu, or A mu, right? Because it's second order in the exponential. So now you get a correlator of A mu and A mu, so you get the 2-point function. So that's non-zero. And then you can go to 3, 4, and if you are smart enough, you can compute the whole series and exponentiate, and you get the answer. The shortcut is that realizing that because Maxwell's theory is abelian, it's a free theory, so it's quadratic. And we know how to do quadratic integrals, right? So we can...
Professor?
Yes?
When we did the expansions, when we found the expansion series for the exponential, I understand why we needed the time ordering, but since it's only one integral now, why do we still?
No, this is just a notation. These are infinitely many integrals, or it depends on which order in the exponential you go. You will have n integrals. So this.
Okay.
So this is a symbol. This. Okay. This is just what happened was that the coefficients in front of each term were 1 over n factorial. So it's like the exponential series. Anyway, so if you remember your path integrals. I'm not going to worry about gauge fixing and all these things. This is just formal computations, okay? Because this is quadratic, we know how to compute it, right? You remember the Gaussian integral, right? There's square root pi over a. That's when it's only quadratic, but if you have a linear and a constant term in the exponent, all you have to do is complete squares, do a change of variables, and you get the same thing, right? But when you complete squares, you get a constant that factors out of the integral and stays there. So what you get here, so if I write now something like that. So J here is an external source, okay? So you can think of it as the linear term in your Gaussian integral. So this is quadratic in A. I'm not writing, but this is f mu of mu nu. So this is quadratic in A. Now a linear term in A. I need to complete squares, blah, blah, blah. And what you get is some normalization factor, which I'm not going to worry about. And then you get e to the double integral dx dy. Of course, these are, let's say, d-dimensional integrals. So I'm not going to write. Well, let's do it in 4 dimensions. So it's and then I get j of x. I get the propagator or the Green's function j of y. Okay, so this is basically a generalization of the formula okay, so you can see A is what's multiplying the quadratic term. So in Maxwell's theory it would be f mu nu, but f mu nu is basically derivative operator. So if you integrate by parts, you can write this as something A Laplacian A or something like that, right? Means invariance and all that stuff. So because you get a 1 over A here, you need the inverse of the Laplacian. You need the inverse of the differential operator that appears in the equation of motion, and that's basically the Green's function. Okay? And then you get x squared, b squared, but b is the linear term, right? Which is j in this formula. Okay? So this is exact. And then for a Wilson line, or for a Wilson loop, j mu of x is something like, I'm not going to write all the factors of 4 pi and all that stuff, something like a delta x minus x path x dot mu. So basically, what is the current for a point particle? Well, the current for a point particle must be localized where the particle is. So that's why there's a delta function here, right? So this is 0 everywhere except at the location of the particle. The particle is moving through some path that I choose, and then it's proportional to the velocity of the particle, right? Times the charge, or whatever you like. It's just a constant of proportionality. So then now I can plug in the Green's function, and I will find that the Wilson loop, in this case, goes like e to the minus q squared. So the q squared comes from the fact that, right, there's a q here. And then I get a double integral. Double integral ds prime. And then I get x dot mu of s, x dot mu of s prime divided by x of s. Okay. Because the Green's function in 4 dimensions is 1 over r squared. Yes. Okay, that's it. Now this is divergent, of course, because at some point these two integrals will go over the same point. But we can regulate that, and okay, now that becomes a whole different story. But there's an example of a Wilson line that you can compute. Okay? Now, as in all areas of physics, this is maybe the only example we can compute exactly. All right? The free theory. Anything beyond the free theory is very, very hard to compute exactly. But actually, Wilson loops can be computed exactly in very, very special cases, and that's why they're attractive. Attractive? No. Interesting. In the context of ADS-CFT. Because Yes.
This is not the integration value, right?
Yes, this is it. I'm being very sloppy with the notation. Sorry. I'm being very sloppy. Sorry. Yes. This is already. This is an expectation value. I see you.
Yeah, I'm thinking because maybe you can use that to calculate the value of A, for example. You write 2 times your current, and you get your
Yes.
function.
Good.
I'm thinking how can I do this calculation to get the expectation value of some value.
It's a dirty trick because you're used to doing this precisely in the way you're thinking.
For A.
I get this and I take true derivative with respect to j. So on this side, that will bring 2 factors of a, and that would be the 2-point function.
Yes.
And then on this side, I will just get g, right? And then put j equal to 0. That's what you've been taught in QFT.
To get the expected value of A.
That's fine. I'm taking advantage of that same formula, but now I'm not putting j equal to 0, and I'm not taking derivatives with respect to j. All I'm saying is that I can compute this integral exactly in j.
So you are putting.
I'm putting one very particular choice of j, which is this.
Okay.
It's kind of a pathological j because it's localized on a curve, right? That's what the delta function does.
We are doing the same, but you are not putting the current to 0. You're putting the
I'm not taking derivatives with respect to j, and then I'm not putting j equal to 0. I'm just plugging in the j that I like, and that mimics, let's say it's a trick that mimics the insertion of a Wilson loop, because what is this guy? This guy is this path integral without this term, but with the trace inserted here, right? There's no trace now because it's abelian, but with the exponential of the integral of a. So I get the product of 2 exponentials. It's the sum of the exponents. Now, one is an integral over space-time, the other one is an integral over the path, but I can do the integral over the path as an integral over space-time with a delta function, and now it looks exactly like this, with j equal to delta function. So it's a trick. Okay? There's another question in the back, but I think it was the same question because I saw the reaction. So, let's go now to n equals 4 superior mills, because I started my lectures by talking about holography, and I mentioned ADS-CFT that equates n equals 4 superior mills with type 2b string theory, right? So n equals 4 superior mills is a Yang-Mills theory with just more fields, okay? I'll write the field content in a moment. But I could define Wilson loops like I just did. It'll be a little different, but I could do that. Okay? And now I can ask myself, are there very particular Wilson loops? Let's say the straight line, a circle, some path that I can choose where by some miracle of life I'm able to compute this expectation value of this one Wilson loop exactly. Okay? Without using perturbation theory, but exactly if you remember, this guy had lambda and n as the 2 parameters in the theory, right? So the 2 coupling and the number of the rank of the gauge group. If for some miracle I'm able to compute at least one Wilson loop for one specific curve exactly in lambda and n, now I have a toy I can play with and compare with string theory calculations. So now I can turn on my ADS-CFT dictionary and see if I get a match between the two. And not just a match at the n equals infinity, lambda infinity limit where everything works beautifully, but maybe get 1 over n corrections and 1 over lambda corrections and see if they match. Okay? So that's my motivation. I pushed you there because that's my area of research, but trust me, this whole technology of Wilson loops is also used in lattice gauge theory and and also in mathematics. Okay? So now I'm going to go to this theory. So this theory is actually a conformal field theory. It's not just any quantum field theory. It's a conformal field theory. I'm not going to go over the whole machinery of CFT. I just mentioned that this is defined in 4-dimensional flat space, Minkowski space, so it's already Poincare invariant by definition, by construction. But that Poincare invariance gets enlarged due to the very balanced combination of fields. Okay, so this manifests itself in saying that the beta function for the Yang-Mills coupling, for example, is 0. So there's no running. So that's a signature that things don't depend on the scale, on the energy scale. Well, the energy scale is the same as making things larger or bigger or smaller. So that's basically a dilatation of space, and that's a signature of conformal invariance. Well, you can show that this is conformal invariant. Actually, I don't know if it's been proven exactly, but certainly to whatever ordinary perturbation theory you want. Maybe, Breno, do you know? Is there a proof that this is exactly conformal? There is. Yes. Anyways, so this is a gauge theory. So this is, we have one field, a mu, right? Which I wrote last lecture, right? So A goes from 1 to n squared minus 1. So this is SUN. Okay? And then in addition to that, you have 6 scalar fields. Okay? One through 6. But they're scalars, but they also carry the same index as the gauge field. Okay? So you can think of them, if this guy's a matrix, when I contract this index with the generators of SUN, so I get rid of the index A just by expanding in some basis, this guy will do exactly the same. So I can think of phi also as a matrix. Okay? If we're in the fundamental representation, it'll be an n by n matrix. And then I get 4 Weyl fermions. So these are scalars, and these are Weyl fermions. Okay, and as well, people say they transform in the adjoint of the gauge group. I don't like that sentence because I think it's wrong, but you'll find it in books. Okay.
What is wrong?
Because I can choose a different representation of the gauge group and write this as a matrix of whatever size I like. It's just the fact that there are as many gauge fields or as many scalars as there are gauge fields, so it's the rank of the gauge group. And that's what they mean. And it's also wrong to say that this guy transforms in the adjoint because this guy is not a vector in any sense. It's a connection. Connections don't transform the same way as tensors. So it's just, okay, I'm not saying it's wrong, but I said it's wrong, but I didn't mean it. It's just an abuse of language, okay? But let's say, for the sake of simplicity, that this is an n by n matrix, so I get rid of that index, n by n matrix, n by n matrix. So I get 1 of these, 6 of these, 4 of these, okay? And you can go to your quantum field theory books and see what the one loop beta function for scalars and for vectors and for fermions and etc. Actually, you can do it exactly in supersymmetric theories. I think it's called the NSVZ beta function. And then you plug in the number of fermions, the number of scalars, and the number of gauge fields with those numbers, and you get exactly 0. Okay? So fermions come with a minus sign, blah, blah, and you get 0. So this is a CFT. Okay? Okay. So this theory has it has SO 2,4 cross SU 4 symmetry. Okay, this is the conformal group. So this is the enlargement of the Poincaré group. So the Poincaré group would be SO3,1 or 1,3 times translations. When this gets enlarged, this becomes SO2,4. Okay? And these translations are in there, trust me. Okay? And then SU4, it's clear because I have 4 fermions, but really SU4 is the same as SO6. Okay, there's no reason why you should know this by heart. And it's just I learned this when I was very young. It's a low dimensional coincidence. SO4 the same as SO6, SO2 the same as SO3, SP5 the same as whatever. Those are lower dimensional coincidences. Okay, there's no pattern. But it is true that SU4 is the same as SO6. So you get that symmetry. You can rotate the scalars among themselves. You can rotate the firms amongst themselves. And this is it's invariant. And this, of course, is the R symmetry of the Soucy algebra. Okay, I'm not going to go over the supersymmetry, but those of you have seen. Okay, so this is okay, and then also it has 32 supercharges. So these are the bosonic charges, so you can compute angular momentum, R charge, etc. are associated. So this is, I'm thinking Nether theorem, right? So for each symmetry you get a conserved charge. Well, these are called odd charges. For this symmetry, I get the full Poincaré charges, so the stress tensor and the angular momentum, etc., and I get other additional charges as well. Energy, Hamiltonian, etc., are all encoded in this. But I also have supersymmetry, so I have fermionic charges, and there's 32 of them. Okay. Okay, I'm not going to write the conformal transformations, but so just to the Lagrangian will be something like, so I'm not going to need it, but would be something like the trace of f squared, of course, for the Yang-Mills fields, and then I get the trace of d phi squared for the scalars. I also need a trace because remember the scalars are also matrices. Okay, so this is d mu phi dagger, traced, etc. And then I get, there's a potential term, which is the trace of the commutator of phi squared. So this is an interacting theory, it's not a free theory. So this is a quartic potential. See, the commutator is quadratic, squared gives a quartic interaction, and of course Yang-Mills interactions are already cubic and quartic themselves. Okay? So this is an interacting theory. So it's not a free theory. So it's worth studying it. Not very realistic. It has conformal symmetry, it has a bunch of fields that I have no idea what they mean physically in the real world, but it has a nice mathematical structure. Maybe we can learn something. Okay?
Professor,
Yes?
the second trace is only the scalar fields is squared, or is the whole thing?
No, this is d phi.
Okay.
D mu phi. It's the standard kinetic term for scalars.
Okay. So another question: the scalar field, I remember for the last class that it transforms as a gauge field because it transforms with, or is it because it transforms with a U matrix, or I am remembering wrong?
No, these guys transform
As scalar fields.
covariantly. Yes.
Oh, covariant.
But not as matter fields, actually. They transform, if you think of them as matrices, they transform with one
Yeah.
element of the gauge group here and the inverse here.
Oh, okay.
But with the point is that not like a mu, remember, also has that term, but then has an additional term with the derivative. So the scalar and the fermions don't have that.
And the Weil fermions, do they transform under a gauge transform?
Yes. So these two transform exactly the same.
Oh, okay.
And then this guy transforms the same as these two with an extra term, which is the G, D, G minus 1, the standard one, right? That's why I don't like saying that it transforms in the adjoint. Yes?
The scalars are in the adjoint representation.
I don't like saying that, but yes, if you read the books, they'll say that. But again, I don't like that because to me, I'm thinking of this guy.
Yeah.
This guy. And then this guy. And I'm not saying which representation I chose the generators.
But they usually work in the adjoint the books.
No, usually you work in the fundamental actually.
Ah, okay.
So the usual most of the calculations are choosing these TAs to be the fundamental of SUM.
So they just mean that they are made.
The language that they are in the adjoint is just that there are as many gauge fields as there are generators.
Ah, okay.
Well, let's put it another way. All these three fields are Lie algebra value.
Yes.
That's the more precise way of saying it. A, phi, and psi are Lie algebra value, but then when I choose a representation of the Lie algebra, they will be matrix value, but whatever size matrix I choose, as long as it's a representation of SUM.
Okay.
Okay. But the standard thing is to think of these guys as n by n matrices. So the adjoint has dimension n squared minus 1 times n squared minus 1 matrices. So it's the adjoint is that representation in which the vector space is the same size as the Lie algebra. The adjoint is that representation in which the vector space is the Lie algebra itself. Okay? So the size of the vectors is the same as the number of generators. But that's one representation. I could choose whatever I like. So, okay. So let's study Wilson loops in this theory. So of course, I could define the Wilson loop exactly the same as I did, but because there are more fields now, so it's not just the gauge field. I have a scalar field. I can play a little bit with this. So in this theory, it makes sense to define what are called Maldacena Wilson loops, because Maldacena thought of this. And they're basically the same, so I will have the trace over some representation R, whichever representation I choose for my fields here. And I will have the path order exponential of I to Young-Mills. But now, instead of just adding the gauge field, as we did before, I could add new couplings to the scalars. Why? Because I can. But there's a good motivation. So this theory can be constructed as a dimensional reduction of n equals 1 super Young-Mills in 10 dimensions. It's a trick. Think of it as a trick. I've never heard or read any physical intuition behind this. So it's just a mathematical trick. Start with in 10 dimensions with n equals 1 Young-Mills. So no scalars, no fermions. Well, no, sorry, fermions, but no scalars. Just a gauge field in 10 dimensions, and then go from 10 to 4. When you split 10 into 4 plus 6, you get the 10-dimensional vectors become a 4-dimensional vector and 6 scalars, right? So you can think of the phi's as the components of the gauge field in 10D, or the remaining components of the gauge field in 10D. And then you can think of, in that same logic, this guy as the same as this guy, but in 10D. So this would be like a curve in R6. Right? Does that make sense? So this would be, I could write this as x dot m a m, where m now goes from 0 to 9, right? And if I split this into 4 plus 6, I just write am as a mu phi I, so 4 and 6 components, and I split xm into x mu and yi, I get this becomes this. Okay? So it makes sense in this theory to just generalize our definition of Wilson loop. So I lose a little bit of the intuition that I mentioned before, but I gain something more. Yes?
What is y in 4 dimensions?
No, in 4 dimensions, it's a 6-dimensional vector that,
But there's no 6-dimensional component.
well, yes, there is. It's not space-time, but there is an internal 6-dimensional space where the scalars live.
So it's a function of x?
Yes. So y, so x mu is a function, is a curve in R4. Don't tell a mathematician I wrote that, but and this guy is also a curve, but in R6. And of course, this is space-time, and this is some internal space where the scalars take value.
SU4?
SU4,
But
SO6.
it should be the manifold of the SU4 or R6?
Let me be more precise. It's neither. This is not the group manifold of SU4 or the group manifold of SO6. It's a space, it's an internal space where SO6 acts as a fundamental representation of SO6. A sextuplet acts on R6. The same group, SO6, has a different representation where it acts on 4 tuplets, complex, and then it acts as SU4. But they're the same group, okay? It's just in different representations. So this is a curve in this R6 space where the scalars live, but it's not the group manifold of SO6 or anything like that. Okay? Again, if you want to justify this, think of it as coming from literally a path in 10-dimensional space-time, and then you say that space-time is split into 4 plus 6. So the first four are the actual space-time, and the other 6 are some internal directions. So this is a natural coupling to the scalars. So these are the famous Wilson-Maldacena loops. And now, I don't know how much time we have left, but how much? 30. Really? I thought I had 3 minutes left. This is very good news.
So I have a question. So that curve is kind of goes from the R4, but it's like 2 curves in 2 different spaces.
Yes, so I can think of it, well, this is just semantics, as one curve in R10, or as one curve in R6 and one curve in R4. But like you said, now this is a function of 2 curves. So let me write that down. Thank you for this is a functional of 2 curves. One in R4 or spacetime, and one and another in R6. And I need to choose, I need to specify those curves to compute the Wilson line or the Wilson loop. You say, which curve do I like best? Depends on what I'm doing. Okay, it's like saying, which point in space-time do you want to compute your correlation functions? Okay, hopefully all of them, but it depends on what I'm doing. Okay, this is the same. Which Wilson loop do you want to compute? Which curves do you want to plug in there? Well, hopefully all of them, but of course that's not possible, so I'll try to do the best I can. So I'm going to focus on the straight line now. Yes?
No, you don't have a physical interpretation. Because
Of what? Of this reduction?
Or this one is an Wilson loop. If you lose,
I lost the physical interpretation the moment I chose n equals 4 superior mills. It's not a physical theory that describes anything like I've seen in the lab.
this part.
Okay, yes, that's a good point. So if I can interpret it, yes, that's a good question. This will be, okay, this is not very intuitive, but it's like having a force that's mediated by a scalar, right? This happens in nuclear physics also, right? You have some scalar particle that mediates. We're not used to that. We always think of forces as gauge fields, mediated by gauge fields. But you can have scalars mediating force, and then what you would be doing here is the net force on the probe particle. So a mu carries some force, phi carries some force. The both of them compete, and this would be if I choose the rectangle, I would be computing the effective potential of these two forces combined. I think that's the physical definition. Thank you for pushing that. I was going to say you can gain some intuition from string theory, but I think that sentence is. There's a similar computation when you compute the strength of the force between two branes and things like that, and then they mediate scalar modes as well. So I guess this could be something. It's funny just to think about string theory as being simpler. Okay, so now we can play here. This is now our playground, and the first question we can ask is what are the simplest Wilson loops we can compute? Okay, so what do we mean by simplest? Well, simplest means those which preserve the most symmetry. Usually, if you want to compute things, you would start with the case that preserves the most symmetries. That's where you have most chances of computing things exactly. Okay? So, I'm gonna leave this here because by symmetry I mean these symmetries here. So I will ask, what is the simplest Wilson line or Wilson loop in what is your guess? So for QED or not for QED, for Maxwell, we computed it exactly for any curve, right? I didn't specify the curve there, I just used a trick. I could compute it for any curve. That's not going to be possible here. This is no longer a free theory, so my Gaussian integral is not available anymore. So, okay, let's think in terms of symmetries. So my space has, or my theory has this very large symmetry. Okay? But that symmetry will be broken if I insert in the path integral, which is what I need to do when I compute an expectation value, this guy. Why will it be broken? Because I have to choose a curve, right? To define this guy, well, actually two curves, and those curves will certainly not be invariant under this. Let's make a trivial example. Take a circle. So this is R3. This room is R3. I have translation symmetry in the three directions, forget about time, three directions, and I have SO3. So that's the symmetry of my theory of my space. And I draw a circle here. Okay? So a circle that lives in this, some radius that lives in this plane. Rotate it. Now do a rotation apply a symmetry transformation to the circle. What happens? Do you get the same circle? Do you get the same curve? You get a different one. It's a different circle. Or take the circle and translate. You get a different circle that's centered at a different point.
It's the same.
Well, but it's not invariant under the transformation. That's the point. Okay? The analogy I always draw for this is think of orbits, planet orbits. Okay? Your theory, your Lagrangian, is invariant under SO3. Do you agree? Yes? Rotations in three-dimensional space. There's three conserved charges we call angular momentum. Right? Perfect. Now think of the solutions. What are the solutions in the Kepler theory? Ellipses, right? What happens if I take an ellipse and rotate it? Do I get the same curve? No, I get another solution for sure. Otherwise, it wouldn't be a symmetry. Okay? Symmetries map solutions to solutions. So I can take an ellipse and I get a different ellipse, for sure. But it's not the same. But there's one exception. What's the exception? The circle. If I take a circle and I rotate not in any direction, not all of the SO3s, but an SO2, I get the same circle. So in that sense, the circular solution is the simplest one in the Kepler theory. Does that make sense? So now the same logic applies in all of physics, really. What is the simplest Wilson loop we can think of? What is the curve that will break the least number of the least amount of symmetries? Someone said it, but the circle?
What, the line maybe? Infinite line.
There's a subtlety here because this is a closed curve. Okay? So it has to be closed in order for it to be gauge invariant, but there's a loophole. I can take an infinite line and then make sure that my gauge transformations die at infinity and it will still be gauge invariant. Okay? So it's a loophole.
How do you make sure that the large gauge transformations?
No, I need to avoid those.
But in the bad integral, how do you?
No.
How do you know that you are taking those away?
In the path integral?
Yeah. You don't gauge the group, but
No, the path integral comes with data that you need to specify, which are boundary conditions. So,
okay.
so it's already it's
In the boundary conditions,
yes.
you put 0 and
Yes.
you
Yes. So once I fix the boundary conditions, there are infinitely many gauge transformations that are not allowed anymore because they will break those boundary conditions. So so that's the explanation. So all I'm saying is that there's a loophole. It doesn't have to be a closed curve. It could be a curve that goes to infinity. Okay? Think of it as closing in infinity. Actually, that's a good way of thinking of it. R4 is the same as S4. You've seen the stereographic projection. So you can think of instead of an infinite line in R4, you can think of this as a closed curve in S4. I agree, there's subtleties because I need to specify boundary conditions and all those things. But if you allow me that fact that it doesn't have to be closed anymore, then this would be the simplest one. Okay? So how many of these symmetries are preserved? This is the same as a circle, by the way, because the theory is conformal. I can map this to a circle. And I won't do that calculation, but it's not that complicated. I could map this to a circle. So, which of these symmetries are preserved by this line? Well, this line will not see the SO4, the SU4. The SU4 is some internal thing that acts on R6. R6 is the scalars and the fermions and blah, blah, blah. So my curve, my x mu, doesn't know anything about SU4. So for the moment, I'll leave it aside. But it does know about SO2,4, which is the conformal group of space. So let's see which symmetries do we preserve.
Dilatation.
So if I take this curve and I multiply all the coordinates by a factor of 100, do I get the same curve?
Yes, it's still a straight line.
Yes, it's still a straight line. It didn't move anywhere. It just got expanded, but because it's infinite, I get the same curve, right? So, good. So I get dilatations. What else?
Translations in
Did everyone hear that?
Yes.
the
Translations along the curve, right? So it's just one translation, right? One. I always get confused with the word translation because it means from one language to the other, which is, in Spanish there's two different words for that. Translación, traducción, but in English it's the same, so I always get confused. Everyone agree? So I can translate my space-time along the direction of the curve, and the curve remains the same, nothing happens. If I translate this way, then the curve moves, right? Great. What else?
Inversion. Nothing, don't go to the.
Let me leave that to the end because that's the least intuitive. There's one that's obvious just by drawing. Rotations around the curve, right? So, that. Okay? How many rotations are those? This is in 4 dimensions. So how many?
3.
SO3, right? Well, it could be SO2,1, depending on which direction I choose the line. So if my line is along a spatial direction, this will be SO2,1, because my rotation would involve time as well. But if my line is in the time direction, then the rotations don't touch time. They just rotate, let's say, X and Y, but leave T invariant, so that would be, well, SO2 I can picture, but you can think of it as SO3 now because in 4D. And then there's one more, well, there's 3 more, which are not very intuitive, okay? Which are the special, which are related to inversions. And I'm not going to spend any time on this, but the conformal group has more terms. So you have rotations or Lorentz group, you got translations, you get dilations, dilatation, and then you get what I call special conformal transformations. And there's 4 of them. And you can think of them as taking a point, making an inversion. An inversion is taking x to 1 over x. Okay? So if I'm in the plane, and this is the origin, this is the point, the transformed point is in the same ray, but has the inverse length. Okay? So I can do an inversion, translation, inversion. Those 3 operations are what's called a special conformal transformation. Okay? And it's not obvious at all, but this guy preserves 3 of them. Okay? No, sorry. 1. Sorry. 1. Thank you. If you sit down and think of this process of inversion, translation, inversion, you can think of which one preserves the line, and you'll find there's only 1 of them. And it's not so intuitive. I'm not good at drawing, so I'm not going to do it. Anyways, these are the symmetries preserved by the line. And they form the group SL2R cross SO3. And this is not obvious at all, but this guy, and this guy form the SL2R group. SL2R is the same as SO2,1 or SO1,2. I was a bit confused. Okay? And then you get the rotations, but it's very intuitive that the rotations don't talk to the other symmetries. They commute. Does that make sense? So if I take my line and I do a translation and then I rotate, it's the same as rotating and then translating. Those 2 commute. And the same with rescalings. Okay? So that's why you get a cross product. There's a subtlety here that I'm assuming the line points in the time direction. That's why this guy is SO3 and this guy is SO2R. But if this guy was in a spatial direction, this guy would be SO3 and this guy would be SO2R or SO2,1. So either way, it's the same. Okay, good. So I get those symmetries. Now, What else could I do? So what about this guy? So I could put this curve y equal to 0. So my curve is just a point in R6. And that would preserve the full SO6. Do you agree? So the origin of R6 is invariant under all of the possible SO6 rotations. That's fine. That would be the most symmetric case, for sure. Now that's kind of boring. Well, because that's just the standard Wilson loop from standard gauge theory. So there's only the A mu, the phi's don't even appear here, which is fine, but I'm losing an opportunity here, which is, okay, I preserve this guy, but there's 32 other charges here that I could preserve. Okay? And the more symmetric, the better. The more chance I have to compute things exactly. Now these charges are fermionic, so my intuition goes out the window. Now I'm not, so this thing that I rotate around the curve or I translate or I do rescalings, I lose that intuition. I don't have my brain is bosonic, okay, so I don't know what to do. But they're there, mathematically, they're there. So I can ask, well, what do I need to do to preserve the most of them? As many as I can, okay? So, and that will make me break some of these as well, okay? So in other words, if I preserve the full SU4 or SO6, I will break all 32 of these guys, okay? That's too many. If I try to preserve some of these, I can, but I need to break some of these. But again, there's more, okay? So,
I'm sorry, I'm not getting what we are breaking exactly, and what we are preserving exactly.
okay. So, maybe these groups are not so intuitive, but let me give you another theory a simpler theory. Just Maxwell theory, okay, in R4. What are the symmetries of that theory? Global, not local. Global symmetries.
U1.
No, U1 is local.
Okay.
What are the global symmetries? Lorentz and Poincaré, right? So full Poincaré invariance. Great. And now, let's say you want to compute a Wilson line or Wilson loop in that theory, Maxwell theory. Okay? You need to give me a curve in space. But then I ask, which curve breaks the least symmetries of these Poincaré group? Does that question make sense?
Okay, and this line is in order to do the Wilson loop.
The Wilson loop comes with the definition. In order to specify the Wilson loop, I need to give you a curve. And it's part of the data that I need to specify at the beginning. Which curve do I want to put there depends on the problem I want to solve.
Yes.
So if I want to compute the quark-antiquark potential or the electron-positron potential, I would do a rectangle.
Yes. Okay.
Right? And I would try my best to compute the VEV of that Wilson loop. And if I manage to do that, I look at the exponent and that I will get Coulomb's law. Okay? Or in QCD, I will get the area law, or whatever. So that's one. The other application that I mentioned is the Arnaud-Bohm effect, and you would detect there's a solenoid there. But really, if you are able to compute all possible Wilson loops somehow, you more or less regain the local theory. Because you can do what's called you can do an expansion of any curve in terms of local operators. So,
one symmetries and one others.
sorry?
One curve will preserve some symmetries while the other.
Yes, but this is the same as in local quantum field theory. So if you, again, Maxwell theory or QED or whatever, if you want to compute the VEV of some operator, right? You need to insert that operator in the path integral. Agree? Now, if that operator inserting the operator in the path integral will break some of the symmetries of the path integral without insertions. Because the path integral without insertions is the action, which has your Poincaré symmetry. We assume that the integration measure is also Poincaré invariant. So that has nice Poincaré things, but if you put something else inside the integral, that something else could break the symmetries in the sense that if I take the symmetries and act on this guy, I don't get the same guy. It's not invariant. So if I insert a local operator, I'm breaking translation invariant for sure, because that depends on the point x. Okay, now that breaking is controlled in the sense that there's word identities and things like that, but the message is that whatever I put in the path integral doesn't usually have all the symmetries of the actions. That's what I'm saying.
Yes.
So now, if I want to compute the VEV of a Wilson loop, the Wilson loop will not have all the symmetries of the action. So because the Wilson loop depends on a curve, I need to look at what symmetries does the curve preserve or break. Okay, that's more or less the message. And then the only difference here is that my theory has more fields, so it has a bigger symmetry. Okay, it's not just point variable. Okay, so let's go to Susie.
Please.
So, okay, there's a lot of machinery here that I'm not going to explain because I don't have the time. But if you know anything about supersymmetry, supersymmetry is a symmetry that relates bosons and fermions. Okay? So the gauge field will transform into into some of the Weyl fermions, and the scalars will also transform into the Weyl fermions, right? And then the Weyl fermions will transform into a combination of scalars and gauge fields. Okay? Now, because my Wilson loop only has the gauge field and the scalar, I only need to specify how those two transform. Okay? So there's one transformation I'm not going to write. Okay? And the easiest way to write this, in order to avoid too much machinery, is to use this 10-dimensional trick. So I'm going to think about A mu and phi as just one gauge field in 10D. Okay? So the transformation will be delta A m. So that's the gauge field in 10 dimensions. Okay? And this will be psi bar gamma m epsilon. Okay? Where this guy is my 10-dimensional fermion. Okay, so this is 10D. That's a fermion or spinner. This guy's a spinner. And these are the 10D Dirac matrices. Okay? That's a simple, actually, in 4 dimensions, Super-Yang-Mills takes exactly the same form. The supersymmetry transformation of Super-Yang-Mills, it's exactly the same. Just replace 10D by 4D. Okay? But the difference is that in 10D, again, this is a trick. You don't have to go to 10D to do this, okay? And this is the shortcut I'm taking to avoid too much machinery. Dirac matrices are 32 by 32 in 10 dimensions. Okay? So I can split the 10 dimensions into 4 and 10, which is what I need to do. So I will get, for the first 4 indices, the transformations for the gauge field, and then for the other 6 values of the index, the 6 scalars, right? And then I have to split the Dirac matrices. And this Dirac matrices will split into SO4 matrices and SO6 Dirac matrices. Okay? And SO4, so in 4D, how big are the Dirac matrices?
4 by 4.
4 by 4. And in 6D? 8 by 8. You don't have to know this, but. And what's 8 times 4? Okay, so that's how you do the split. Okay? Anyways, these are the Susi transformations. And now, I ask myself, what choices of epsilon, this is a constant, well, actually, so, can I choose epsilon? So epsilon is like my transformation parameter. So in bosonic symmetries in SO3, these are the three Euler angles, let's say. Okay? Or the rapidity of the boost I'm doing in a Lorentz transformation. These are the transformation parameters. So in supersymmetry, the transformation parameters are fermionic. Okay? So they're spinors. So can I choose epsilon such that x dot mu delta a mu plus yi delta phi I is 0. Now y, this is the exponent in the Wilson loop, right? Remember the Wilson loop is the path order exponential of this guy without the deltas. So I'm asking, is there some transformation that leaves the exponent invariant? If that's the case, then the Wilson loop is invariant, and I will preserve those symmetries in the path integral. Yes? Does that make sense? Actually, I could have written the same thing, but for the bosonic ones. And I will get the answer that we wrote here. So I could ask the same question, but now transform x, a, y, and phi, and find these, well, actually y doesn't transform. But I could transform x, x, a, and phi, and then find that those preserve the straight line. So this will be x dot mu psi bar gamma mu epsilon plus yi psi bar gamma I epsilon equal to 0. Okay? I'm just using this. All I did was split m into mu and I. Okay? So the first 4 components are called A, the other 6 components are called phi, so I just read what they are. Now, what I'll do here is that I will write yi as the norm of x dot times some vector n. Okay, this is not strictly necessary, but if you recall, this goes inside an integral ds, and in order for it to be reparametrization invariant, y has to transform the same as x dot. So I'm just pulling out that dependence, and I'm calling the rest n. And it's not a big deal. The point is that now I get the condition x dot mu, gamma mu, plus norm of x dot n I, gamma I, acting on epsilon equal to 0. Because I want this to be 0 for any fermion, of course. Not remember the fermion, this is inserted inside the path integral, it's integrated over psi, so psi is whatever I want it to be. So I can just get rid of psi, and I get this condition here. So the question is, are there epsilons that satisfy this? Because it could be, if I choose a very complicated curve, so there's dependence on the curve here and here, or curves actually, the solution to this would be epsilon equals 0. So let's see. My name,
2 minutes.
you can interrupt me
You have 2 minutes.
in 20 more minutes. So, if this is true, then it's also true if I square this, that also has to be 0. Do you agree? So, I will get some condition if I take x dot mu, gamma mu, plus x squared, and actually, if you use the Clifford algebra for the gamma matrices, you will find that this is proportional to the identity, and it's actually x dot squared plus norm of x dot squared times n squared. This is just an identity, okay? You can do this at home, but remember these two anti-commute because they're 10-dimensional Dirac matrices with different indices, so they anti-commute. So when the cross product will cancel, and then this squared is eta mu, this squared is delta ij, so you get that thing. So the important thing is that this is proportional to the identity 32 times 32.
Sorry, you take the square of that square.
Of this guy.
And that will be the
That's-
value of x dot?
Yes.
No, the absolute value. X dot.
No, it's just that I wrote this. So there's an x dot there. Does that make sense?
Yeah.
So you mean why do I put this? Because it could be time-like. So there's a sign there that I don't know. So I'm just putting the absolute. Yeah, let me just finish quickly. The point is that if this is true, then it's also true if I multiply this by the same matrix, right? But if I multiply this by the same matrix, I get that matrix. But this matrix is proportional to the identity, so it won't depend on epsilon. So I need this to be 0. Does that make sense? It could have been, before I did the calculation, that whatever matrix here, when I square it, it's not the identity, right? Well, if it's not the identity, then that gives me one more restriction to epsilon. Well, it's not an additional restriction, but it's included, of course, here. This is the general one. But it could have been that I get a non-trivial equation for epsilon. Does that make sense? Now, if this guy was not proportional to the identity, I couldn't say that the matrix is exactly 0. It's the matrix acting on epsilon that's 0. But because that matrix is the identity, the matrix has to be 0. Or proportional to the identity. This has to be 0. So here I learned that x mu has to be time-like. Okay? And I also learned that n squared has to be the unit vector, or a unit vector. I'll finish here. This is just the fact that these two have the same norm. If I take let's say I take the absolute value of this equation, I get this, right? So I learned that n has to be a unit vector, and that x has to be time-like. So this line that we drew has to be in the time direction. So the SL2R and SL3 that I wrote there are correct. Okay? If it had been in some space direction, I would need to do some small changes. So I will end here. Next lecture, I will show you that these guys have to be constant, because instead of squaring this, I can take the derivative of this, okay? And then I'll find that it's constant, and that I will find that only half of the possible epsilons are allowed, okay? That will be next lecture. Thank you.